All right, so we're gearing up for our circuits test, which is just going to be one circuit, a little smaller than the practice one we have here. This is 28 resistors and 8 junctions in a 36-volt system. Remember, what we're trying to do is combine all of those 28 resistors into one equivalent resistor that would do the same work so that we can find the total current. And we always start by redrawing the circuit as though it were in a line and all the resistors were horizontal. That makes it easier for us to tell what's parallel and what's in series. And we have these two equations. If the resistors are in series, we can simply add them up to combine them. No matter how many they are, as long as they're all in series, we can combine them by adding their resistance. If they're in parallel, we can add up the reciprocals of those resistors, and once we get that done, we can then take the reciprocal of that to find the resistance of everything in parallel. And once we get it down to one equivalent resistor, we use Ohm's law here to find the total current, and then we use the two rules in red here to go back up through our drawings and back up to find the voltage and current at every single one of the individual resistors. So let's get started here. I'm just going to start with the redrawing of this 28 resistor circuit. Okay, and you've got to make sure that you really want to keep all those junctions in there and make sure that everything joins up correctly and in the right spot. So the electrons come out of that 36-volt source. They come to junction 1 where they have a choice to go through 3 separate series of 2 resistors that all, in those 3 series, all happen to be in parallel with each other. They join back together at junction 2 to go through resistor 7. At junction 3, it splits off where it can either go through resistors 17, 18, and 19 in series, or through 8 and 9 in series, and then split again at junction 4 to go through this 3 resistor series, which is in parallel with resistor 13. Rejoin up at 5, where it all goes through resistors 14, 15, and 16, and rejoins where it had split off at junction 3, rejoins at junction 6, goes through resistors 20 and 21 in series. At junction 7, it has a choice to go through any one of these 3. The top 3 are in series. There's one lone resistor in the middle, and the top 3 in series, and then those 3 sets are all in parallel, rejoining at junction 8 and on into the end of the battery. So now we can start collapsing. And remember, you can only collapse and combine resistors if everything you're combining is series or everything you're combining is parallel. You cannot do them both at the same time. We don't have equations for that. So here, what I'm going to do is I'm going to do a whole bunch of series all at once. Resistors 1 and 2 can be added to an 8 ohm, 3 and 4, and 5 and 6 can also be added to separate 8 ohm resistors. Resistors 8 and 9 can be added together, 14, 15, and 16 can be added together, 10, 11, and 12, 17, 18, and 19, 20 and 21, and then this set of 3 on top here and this set of 3 in series can all be redrawn as though they were just one resistor, just simply by adding. So we've significantly lowered the number of resistors that we need, and then we can start to talk about what we can do on our next step. Well, you can't do anything resistor 7 because it's by itself. Resistor 8/9 is also by itself. 17 to 19, this one here, this 11 ohm, and this 8 ohm, they're all by themselves. We can't do anything to them right now, but we have these 3 resistors here at the beginning between junctions 1 and 2 that are in parallel, so we can add them. We can take 1/8 plus 1/8 plus 1/8 and then get an answer and then take the reciprocal of that. We can do the same for these here in the middle, the 12 and the 8 ohm, so 1/12 plus 1/8, and then take the reciprocal of that. And these 3 at the end between junctions 7 and 8, 1/9 plus 1/3 plus 1/9, and take the reciprocal. And now we're getting much, much closer, but there's still things that we have to do in order. You could certainly combine these first 2. I'm not going to do that in this step, and you can combine these last 2. I'll hold off on that. I can't do anything with this 12 ohm resistor because it's in parallel with this set of series, so I can't combine them. But I can do these three in series here by just adding them up. 5 and 4.8 and 11 gives me a single 20.8 ohm resistor. Now, still, I'm kind of limited by what I can do, but I have this individual and this individual, this 20.8 and this 12, that are in parallel. So I can do the reciprocal rule, 1 over 20.8 plus 1 over 12, get that answer, and then take the reciprocal, and end up with a single 7.6 ohm resistor. Now I'm down to just 5 resistors in series. I can go ahead and just add them up and get a single 21.1 ohm resistor. So this 36 volt battery, it has 36 volts pushing electrons through that 28 resistor circuit, but those 28 resistors in that pattern can be replaced by a single 21.1 ohm resistor. That allows us to use Ohm's law. Because current is voltage over resistance, we can do 36 volts over 21.1 ohms and get that the total current in the system is 1.7 amps. And that gets us about halfway there. So now you get to go back up through and find the current and the voltage at every single resistor along the way. All right, so here, and we have our two rules. We know that for parallel circuits, the voltage is the same. For series circuits, the current is the same. So what I'm going to do right here is this one resistor was actually these 5 in series. So it expands to these 5. So since they are in series, that means the current is the same. So if this one was 1.7 amps, then all of these are 1.7 amps. And now that means for each of these 5, I have the resistance and the current. So I can solve for voltage. Voltage is resistance times current, so I just do that for every single one of them, and you'll do that every time. You'll take one value, either amperage to series, or take voltage up to parallel, and then you'll solve for the other one, the one you do not have. Okay? And then my next step up, the only thing I did was that this one resistor was actually these two in parallel. So the parallel law says that for parallel circuits, the voltage is the same. So if this is 12.9 volts, then I know that these two are both 12.9 volts because these two in parallel were combined to this single one. And then once I have voltage and resistance, I can solve for current. Current is voltage divided by resistance. Okay, now I just need to keep going back up through. And if you'll bear with me, this is going to go kind of fast. But I'll be taking values from these drawings up to here. So I know that 4.6 volt, this one right here, this 4.6 volt for resistor 1 through 6, was actually these 3 in parallel. So that means the voltage comes up with me, and I solve for the current. And since they're all the same resistance and the same voltage, they all have the same current. And each one of these 3 was actually a part of a series. So that 0.58 volts or amps from all of them is carried up to these series, each of the 3 series, and then I get to solve for voltage, and they'll all be the same because 0.58 times 4 for all of them is 2.3 volts. And I'm just going to keep bringing values up from the other page or from the previous page of this one. I know that this one resistor that was 8 through 16 was actually these 3 in series, so that 0.62 amps is carried up to these 3 series resistors, and I solve for voltage. Voltage is current times resistance, so 3.1 down here, 3, and 6.8 volts. I just need to keep going. This one resistor, 8-9, was actually these 2 resistors in series, so I'm going to take the current with me, solve for voltage. This one, 7 through 19, was actually, or 17 through 19 was actually these 3 in series, so this 1.1 amps gets carried up here, and I solve for volts. This one, resistor 10-13, was actually these 2 in parallel, so the 3 volts gets carried up, and I solve for current. And since resistor 10/12 was actually these three in series, I take that 0.25 amps to all three of them and solve for volts. 0.25 times 4 is 1 volt. I know that my resistor 14-16 was actually these three in series, so I take my 0.62 amps, carry it up there to those three, solve for volts. 0.62 times 3, and then times 5. And I just keep going. I know that I had one before where resistors 20 and 21 had a current of 1.7 amps, and they are actually two in series, so the 1.7 amps was carried up here. I solve for voltage. I have previously solved for resistors 22 to 28, and this one resistor was actually 3 in parallel, so I take the 3.1 volts up, apply it to all three of them, because for voltage, for parallel circuits, voltage is the same everywhere, and I solve for current. And that means the one in the middle, resistor 25, is by itself and is done, but the top one, resistors 22 to 24, was these three in series, and the bottom one, 26 to 28, another 0.34 amps, was these three in series, so I carry the 0.34 amps up to both of them and solve for voltage everywhere.